So Cauchy's theorem says that if f is analytic on and everywhere inside a simple closed loop gamma, then the integral of f around that closed loop is 0. So we've just seen an example of that. What do we mean by simple closed loop curve? Well, it's basically any loop which doesn't intersect itself. So if I draw a picture like this, and that doesn't intersect itself, then that's a simple closed curve. A figure of 8 is an example of something which is not a simple closed curve. But in fact, if you wanted to integrate around something which isn't a simple closed curve, you can actually just split it into lots of simple closed curves. So it's actually not a big problem. Right, so where does this come from? Where does this result come from? So we consider integrating a function f around a closed loop gamma, and we write f as a sum of a real part and an imaginary part. Okay, so we met u and v before when we were talking about the Cauchy-Riemann conditions. So this is f, u plus iv, and dz as before we write as dx plus I dy. Then we just multiply out these brackets. So the real part is going to be u times dx plus the I times I will give us a minus, and it's v dy. And the imaginary part, we can take the I outside, is obviously going to be v dx plus u dy, which gives us this. Then we use Green's theorem, which states that if a sub x and a sub y are differentiable functions of x and y, then we have this result here. This result, if you haven't seen it before, is actually quite easy to prove using Stokes' theorem from vector analysis. This is basically a component of curl, and this is just a line integral. Okay, so we have that result which we can immediately apply. So we end up with ax is u and ay is minus v. Okay, so that's going to give us what happens to ax? So we get du by dy. That's going to give us du by dy, which is what we see here. We're sorry, the minus sign. And we've got a minus v for ay, so that's going to give us minus dv by dx. So we end up with that for this term, and applying this to here, we've got v for ax, so that gives us minus dv by dy, which we've got here, and then we've got u is equal to ay, so that gives us du by dx, the plus sign. So that gives us this expression here. So finally, we know that if f of z is analytic on and inside gamma, then u and v, the real and imaginary parts of a function, must satisfy the Cauchy-Riemann equations. Now the Cauchy-Riemann equations are that du by dx equals dv by dy, which means if that's true, this is 0. And the other Cauchy-Riemann equation is that du by dy is equal to minus dv by dx, which if that's true, this is also 0. So we've shown therefore that if f is analytic everywhere, then these will be 0 everywhere, and therefore this surface integral will be 0, and we find this is 0.